So in an artificial neuron, we get inspired by whatever happens in the real biological neuron. So there are these dendrites, then there is a processing, then it goes to some other neurons, some other nerves, right? So that's what we are seeing, and therefore we mimic this whole idea by a simple thing like this artificial neuron, where we say we have some inputs, okay, which are something like dendrites, and these inputs are going to be weighted, right, so that I know whether I should give importance to some of them, all of them, do I have to give more importance to one compared to another. So these decisions are going to be made, okay. So there is an input stimulus, right. So stimuli are basically a set of inputs that you are going to get. So each of these are like a stimulus, some input that you are going to get. Each of that input gets strengthened or weakened or completely cut off or extremely made high by some weight, okay, here. So some number, if I multiply by 10,000 or something, that's going to blow up. If I multiply by 10 to the power of -6 or something, that is going to play it down a lot, right. So that means don't worry about that particular input, kind of thing. So it's looking at what is important, what is not important, right. How are we going to decide what is important? How do I know the weights? We are going to learn that is what we are going to learn. That's called training the neural network. So the neuron, the cell itself has two parts, okay. One is it's taking a weighted combination. So remember, there's a weight here, weighted combination of the inputs. So let us say the input is x1, x2, x3. I'm going to weight with the number w1. So weight 1 multiplying the input x1, so that gives me another number, plus w2, another weight for this second input x2, plus w3 x3. So now I added three numbers, so that addition is what I am talking about here, okay. So we often also have a bias, don't worry, that's just a little more complication, okay. So this is basically taking a weighted combination of inputs. So when I am multiplying, I am not squaring it or doing anything. So it's a simple linear combination, right. So therefore I am not doing anything great, it is just a linear combination of inputs, right. And classical techniques normally operate in that kind of a framework. Where the beauty of the neuron comes is in what's called the non-linearity. So it is going to operate or do some non-linear operation. So it's not linear, like y equals x, right, y equals mx plus c. You are trying to, it is somehow dependent on the input, but it's not, it's kind of a linear relation, right. So some weighted combination plus some bias or some offset you are going to give, right. That's all you are providing, right. But this neuron, if it has a non-linearity, right, if I give y equals x squared, right, or something else, right, then I am operating in a non-linear fashion, right. And you will see that in neurons, this non-linearity is what gives the power of neural networks. So the deep learning, the whole field has evolved because of the non-linearity, and previously people have worried about non-linear processing, non-linear signal processing, but it was never clear what non-linear function I should choose. So that was and what is optimal, what is not optimal. So that was the kind of thing that was holding back this whole area, and now we see that this is all sort of learnt in some way, okay. And then the neural networks have been found to be very, very powerful. They can solve complicated pattern recognition problems, okay, and that is where the beauty of the neural networks have come about, okay. So once I apply the non-linear, so I had a linear combination of inputs that summed up, so that's again a number. I apply a non-linearity on the number, right, and then I get an output. So the number is output. This number can of course be fed now to other neurons. So the same number will get fed. So these are like your axon terminals, okay. So that's what you're doing, and it can feed other neurons, okay. So this is exactly what we are talking about. So this is called the perceptron. So this whole idea, let me make that laser pointer, okay. We're talking about this guy, okay. So and I told you Frank Rosenblatt, he was a very colorful character, and he made a very, very big claims, I would say. And so he said eventually, so translation, there was a war going on, right, World War II and so on. So he said, you can translate here very easily, machines can do everything in the world, right? And of course, people are spying, right? So German, what was the German saying? What was the French guy saying? What was the Russian saying? So you wanted to know all of these things, right? So, but as I said, it was a cycle. Then Minsky and Puppet, I mean, 1960, 69, 68, the MIT professor made some observations that set back the whole thing, the area. Uh, but since the 80s, as I said, Jeffrey Hinton, kept at it, and it's since 2008 it has really taken off. Okay, so now, so this is my input. So I can have any number of inputs. It can be 100, 200, 300, whatever you want, right? So so these are my inputs. Okay, then next I'm going to multiply that input by a set of weights, right? So some of these inputs might be more important for me. How am I going to know? That is part of the learning process, the training, right? And so therefore I get when I take a linear combination of inputs, this is linear, right? I'm not squaring or doing anything. So this linear combination will give me a number, right, which I call as Z. Okay, so G of all this input, a function of all these inputs, these input numbers which are weighted by the appropriate weights, give me another number which I am calling Z. Okay. Now till here, this is almost like the conventional signal processing or conventional data processing approaches that we have talked about pre neural net kind of approaches. Okay, so these would normally give rise to what is called a linear separation. Okay, so in a two-dimensional plane, if you're separating two classes, remember you talked about heights and weights, right? You saw that the threshold was one point, right? Because we are talking about one line, so the point separates male and female. When I took the two-dimensional heights and weights, usually we have a line that separates the male gender from the female gender. So most of our methods, right, would give you a line, a linear kind of a hyperplane, right? This linear decision boundary between two classes. Okay, and so this is something that we had always dealt with. The power of the neural networks, I keep harping, is because of this non-linearity. Now what happens is that Z, which is a number, is going to go through a non-linear transformation. Okay, so for example, I can have it some kind of a step function that if it is above the threshold, if it is above the threshold, then it will be 1. If it is below a threshold, it will be 0. So the output Y will be only two quantities, 0 or 1. Whenever the Z is above a certain quantity theta, it will be called 1. If it is below, it is 0. So Y is now having only two values, 0 and 1. So the Z could take any values. Now that whole thing has been transformed non-linearly to Y. Okay, and therefore so neural networks, as I said, can solve linear problems also, and later on we'll see it can solve non-linearly separable ideas also. So then things like I'll tell you why this came about. So this is where that Minsky and Puppet, all of these guys, I mean their idea sort of disturbed many of them, and they gave up on the perceptron at least. Okay, so you remember this is I could also do simple operations like AND, right? So if you gave me two inputs, right? So how does an AND function work? And like we're talking about bits 0 and 0, right? 0 and 1. 0 and 1 will always be this. I mean, did they do that correctly? Yeah, sorry. So the what does it do here? Yeah, so you have to weight them actually. So this is not correctly dealt with. So how does an AND function work? 0 and 0 will give you 0. 0 and 1 will give you 0. 1 and 0 will give you 0. 1 and 1 will give you 1. So if you look at the inputs, there are 3 that always give an output 0 and 1 that gives an output 1, right? One of the 4 inputs that are possible, right? So these 3 belong to one class, right? They always will give rise to a 0, right, in the AND function, and this is the only guy that will give rise to 1, right? So if I am looking at a pattern classification problem, so the output will be 0 or 1. There are only 2 classes. So which all give rise to 0 and which all give rise to 1. That is the question. So we will see that 0 1 is always going to, because AND function will give you 0, 0 0 and 1 0, all of them will give rise to 0, and 1 1 is a different class. So you if you want to separate out these two classes, you can put a line somewhere here. I mean, you can put a line to the left of this, and that will separate the two classes. This is linearly separable, right? Or function is the opposite, right? So as long as even one of the two inputs are 1, I'm always going to output 1. So 1 and 0 will give you 1, 1 and 1 will give you 1, 0 and 1 will give you 1, and 0 and 0 will always give you 0, right? So now this is the odd one out. This will always give you an output of 0. The other 3 always give you an output of 1, right? So these 3 we can say belong to one class, and this belongs to one class, and again you can see I can put a line to separate the two classes. Okay, so that is a basic idea here. Okay, but this is where so you look at these two guys, right? So now what Minsky and Papert said was that so this is the XOR problem, right? This is where they told that if you have simple XOR problem, so if I have input 0 0 XOR, right, either exclusively OR, right? So 0 1 or 0 is going to give 1, 0 or 1 is going to give 1, 1 and 1 exclusive, it's not exclusive, so again it will give you 0, right? So if you look at the XOR problem, right, two of them 0 0 and 1 1 belong to the red category, if I want to call that as zeros, and blue, which is 0 1 and 1 0, are going to output 1, right? They belong to a separate category. Now there is no line, one single line that can separate the two classes. If I put a line like this, there's a blue and red belonging to one class. That cannot happen. You want to separate the blue from the red class, correct? If I draw a line like this, any way that I drawn, I cannot separate the blue from the red by a single line, right? And therefore, he immediately he pointed out, however I do, whatever perceptron idea that I do, right? Perceptron idea is what? That if I take a linear combination of the inputs, and take a non-linearity, in this case it's 0 or 1, right? So that thresholding is all that I have to decide, right? You could solve the AND problem and you could solve the OR problem, but you cannot solve the XOR problem. So Minsky just made an observation that no, simple XOR problem itself cannot be solved. What is this Rosenblatt talking about? Perceptron doing it, right? He never said that the neural networks, I mean, the single perceptron cannot do that, right? But somehow that whole thing got lost in everything, and people just said, oh, this doesn't work, right? So that's also happened because whatever Rosenblatt claimed over the ensuing years, it actually did not reflect in a big gain at the ground level. We could not have automatic translation happening. Germans could understand. I mean, you could just understand. So it's still we are struggling with translation, correct? Or even transcription, speech to text, right? So so that is where it took a back seat, okay? But it's the only question is, if I had only one neuron, then okay, there was a perceptron, then there was a problem. But if you had much more complicated setup, then you can solve the XOR problem, okay? So it's just that the multi-layer kind of an idea and multiple nodes kind of an idea. He did not say that you cannot do that. I mean, all that he said is with the perceptron you cannot do it. He himself actually pointed out with to some kind of a more neurons, perceptrons, you can actually solve the problem, okay? But somehow it took a very negative thing and it did not take off, okay? So so for example, in the XOR case, so this is this XOR case. Yeah, this is the XOR case, right? So if you look at this case that you want, right? So he is talking about what are the H1, H2, weights 1, weight 2, and so on, right? So basically these are your called the input. I'll talk about it a little. These kind of architectures you will see somewhat it reminds you of the hidden Markov boundary. You're talking about states and the transition probabilities, right, the edges and all. So it is similar here, right, except that the states are basically actually a neuron. So there is going to be a processing that is done within that round circle, that node, where first a linear combination will happen and then a non-linearity will happen, and it will output a particular number. Okay, that's what each neuron is going to do. It's going to take a number, right, which is weighted already. It's going to take a combination of these numbers, weight them, get a number. That number will go through a non-linearity and it will output a number. That's what a neuron keeps doing. That's all. Okay, a perceptron. Okay. So if you choose these things wisely, okay, it is possible that your output will be perfect. That why it will come like an XOR. So this is your input. X1 and X2 are input. So this is called the input, and normally we put again nodes there, what we call as input nodes. Those nodes, in the case of the input node, we don't do any change. So it's like a identity, it just passes through. Just for drawing purposes, to make it look nice, we introduce that. So these input nodes just take the input and just pass it out. Okay, so they are like an identity node. There's no non-linearity or anything there. But all the other nodes, right, will have some first a linear combination happening and then a non-linearity happening. Okay, and the final node also will have a similar thing. We'll come to it. Okay, so there we'll have a thresholding also happening. Okay, so so why did it? I mean, there are formal proofs that show that with sufficient so with a single layer you can classify with so this two class, the XR problem, which are like this, right? So it's hyperplanes can separate, but even if you have two layers, then the XR problem kind of thing gets started getting solved. And if you have three or more layers, then there are formal proofs that show that arbitrary boundaries can. So if you have two classes that are, you can have multiple classes. I'm talking about two classes. So if they are even really very complicated decision boundaries, those can be solved by this. So these are non-linearly separable problems, right? These can be solved by multiple layers of a neural network, right? So that's the whole idea.